In the silence between stars, there exists a world that whispers of what might have been. A planet caught between two destinies, suspended in the rust-colored dreams of an ancient past. Tonight, we journey there together. Welcome to Whisper Logic. This is a place where you can let go of the day's tensions, where complexity becomes clarity, and where the vast mysteries of our cosmos can wash over you like a gentle tide. I'm so glad you're here. Find a comfortable position, let your breathing slow, and allow yourself to drift with me across the dark expanse to our neighboring world. Mars. Birth of a different world. Mars hangs in the darkness like a frozen moment in time. And perhaps, in many ways, that's exactly what it is. Scientists sometimes call it a failed Earth, though that word, failed, carries a harshness that doesn't quite capture the truth. Mars isn't a failure. It's simply different. A world that took another path, one that diverged from our own so early, so fundamentally, that its entire story became something else entirely. Imagine two siblings, born from the same stellar nursery, wrapped in the same clouds of dust and gas. One grew robust and alive. The other remained smaller, quieter, caught in an eternal stillness. Mars is Earth's sibling, yes, but one whose fate was written in those first chaotic moments of formation, when the solar system was young and violent and everything hung in the balance. When you look at Mars, really look at it, something seems wrong. The planet is divided. The northern hemisphere sits low, smooth, a vast plain that stretches endlessly beneath a thinner crust. The southern hemisphere rises high, ancient and cratered, thick with the scars of billions of years. This division, this strange asymmetry, is called the hemispheric dichotomy, and it's one of Mars' deepest mysteries. What could split a world so completely in two? The answer may lie in violence. The northern lowlands, that great smooth expanse, may not be many impacts at all. It may be one colossal, world-shaping collision in the planet's infancy. Imagine an object, perhaps as large as Earth's moon, slamming into the young Mars with such force that it stripped away the northern crust entirely, leaving behind a basin so vast it encompasses nearly half the planet. This wasn't just an impact. It was a moment of transformation, a single event that would echo through billions of years, determining the shape, the chemistry, the very fate of the world it struck. Deep beneath Mars' surface, hidden in the mantle itself, evidence of that ancient violence remains. The planet's interior still preserves debris from those early impacts, fragments of a chaotic birth locked away in stone and silence. Mars remembers. Its body carries the memory of those collisions like scars that never fully healed. And in those early days, something remarkable happened. Something that would have lasting consequences for the world Mars might become. The planet's dynamo, the churning, convecting iron core that generates magnetic fields, sparked to life extremely early. Perhaps within the first few 100 million years of Mars' existence, its heart was already beating, already creating the invisible shield that would wrap around the young planet. Mars once had a global magnetic field. Not a weak one, not a fleeting thing, but a long-lived, powerful field that surrounded the entire planet for hundreds of millions of years, perhaps longer. In that era, Mars was protected. Its atmosphere was shielded from the relentless solar wind. Water could remain on its surface without being stripped away molecule by molecule into space. For a time, Mars was a world where things were possible. That ancient magnetic field behaved much like Earth's does today. It flipped. The North Pole became the South. The South became the North. Over and over, the planet's magnetic polarity reversed, just as ours has done hundreds of times throughout Earth's history. We know this because the evidence is written in the rocks themselves. In certain regions of Mars' ancient crust, scientists have detected magnetic stripes, patterns of magnetized rock that record the direction of the field when the crust formed and cooled. These stripes are hauntingly similar to those found on Earth's ocean floors, where tectonic plates spread apart and new crust forms, locking in a record of magnetic reversals. Could Mars have once had plate tectonics? Could its surface have been mobile, shifting, renewing itself the way Earth's does? The magnetic stripes suggest something plate-like may have been happening in Mars' earliest days. Not the full, robust system Earth has maintained for billions of years, but perhaps the beginning of one. A geological adolescence that never quite matured. These crustal magnetic stripes record multiple reversals, a chronicle written in iron and stone, telling us that Mars' magnetic field was active, dynamic, complex. And then, it stopped. The dynamo shut down. The magnetic field collapsed. And Mars became vulnerable in a way it had never been before. But why? What kills a planet's magnetic heart? Part of the answer may lie in Mars' lithosphere, the rigid outer shell of the planet. It's unusually thick compared to Earth's, perhaps because Mars cooled faster, being smaller and farther from the Sun. As the lithosphere thickened, it may have acted like a blanket, insulating the interior, choking off the heat flow that drives convection in the core. Without that vigorous churning, the dynamo sputtered and died. The crust itself is chemically odd, different from Earth's in ways that reveal a unique geological history. Mars rocks tell stories of different processes, different conditions, a world that evolved under different rules. The basalts, the minerals, the ratios of elements, all of it speaks to a planet that is not simply a smaller Earth, but something fundamentally distinct. And then there's the color. That famous, iconic red. When we think of Mars, we think of rust, of oxidized iron, of a world bleeding into the cosmos. But here's something beautiful and strange. The red is only skin deep. It's a surface varnish, a thin coating of oxidized dust that has accumulated over eons, blown around the planet by endless winds, settling into every crevice and crater. Beneath that red veil, Mars is not red at all. Its bulk is gray and brown, volcanic rock and ancient minerals. The red we see is merely the face Mars shows to the universe, a mask worn so long it has become the planet's identity. But it's not the truth of what Mars is. It's simply what Mars has become. And so we end this first chapter of our journey with a portrait of a world defined by its early fate. A planet that might have been Earth's twin, that started with many of the same ingredients, the same potential, but whose story diverged in those first violent, formative moments. A smaller world that cooled faster, whose dynamo burned bright and then went dark, whose crust froze thick and still. Mars is a world of what-ifs and might-have-beens. But it's also a world of profound beauty, of mysteries written in stone and magnetism, of a history we're only beginning to read. As you rest now, imagine standing on that ancient, cratered southern highland, looking north across the great dichotomy toward the vast, smooth plains. Imagine the silence, the stillness, the thin whisper of wind carrying red dust across a landscape unchanged for billions of years. Mars waits, patient, silent, keeping its secrets, and we've only just begun to listen. A quiet heart. Beneath the rust-colored surface, beneath the ancient craters and the windswept plains, Mars holds its deepest secrets. To understand a world, you must look inward. You must listen to its heart, feel the rhythm of its interior, trace the slow movements of rock and metal that have shaped everything above. Tonight, we descend, not with drills or machines, but with something more elegant, with waves, with vibrations, With the patient language of seismology, we learn to hear what Mars whispers from within. For decades, Mars' interior was a mystery wrapped in stone. We could see its surface in exquisite detail, map every crater and canyon, but what lay beneath remained hidden. Then came the Marsquakes, gentle tremors rippling through the planet's body, carrying information from deep within, traveling through layers of rock and metal, each layer changing the waves in subtle, telltale ways. And from those whispers, we've learned something remarkable. We now know the radius of Mars' core with extraordinary precision. It extends roughly 1,800 kilometers from the planet center, larger than scientists initially expected for a world this size. But size is only part of the story. Composition matters just as much. The core is not pure iron. It's lighter than that, enriched with sulfur and perhaps other elements, oxygen, carbon, hydrogen, dissolved into the molten metal like secrets stirred into liquid. This chemistry tells us about the conditions when Mars formed, about what materials were available in this part of the early solar system, about the temperature and pressure of planetary birth. Above the core, in the deep mantle, seismic waves reveal something unexpected. A low-velocity zone exists in the upper mantle, a region where waves slow down, where rock behaves differently. This suggests partial melting, or perhaps rock that's unusually hot or chemically distinct. It's a boundary, a transition between the deeper, more rigid mantle and the layers above. Earth has similar zones, regions where the mantle becomes slightly plastic, where convection currents can move more freely. But Mars is smaller, colder. Its interior should be more sluggish, more frozen. Yet here, in the upper mantle, we find evidence of complexity, of layering, of a planet that refuses to be entirely simple. The mantle remembers motion. Even now, billions of years after Mars' most active period, the rocks retain the ghost of ancient convection, the memory of when heat rose and cooled rock descended, when the planet's interior churned with slow, powerful currents. Moving upward, we encounter the crust itself. And here, too, Mars surprises us. Low-velocity layers exist in the upper crust, regions where seismic waves slow unexpectedly. These may be zones of fractured, porous rock, the legacy of ancient impacts that shattered the surface, creating networks of cracks and voids that never fully healed. Or they might be something else entirely. Layers of different composition, perhaps. Regions where volcanic material intruded and cooled. Each possibility opens another window into Mars' geological past, another piece of the puzzle. Deeper in the crust, in the middle depths, there are hints of saturation zones. Places where water or ice might fill the spaces between rocks, where frozen moisture has been trapped for eons, preserved in the cold darkness. These are not flowing aquifers, not underground rivers. They're static, frozen archives. Water locked in place, waiting. Every piece of this picture comes from Marsquakes. The planet trembles, rarely but persistently. Not with the vigor of Earth's tectonics. Mars has no shifting plates, no subduction zones grinding against each other, but with its own quiet seismicity. Impacts from meteorites. The slow settling of ancient faults. The subtle contraction of a cooling world. Each quake sends waves spiraling through the interior, and each wave carries data. Scientists measure the arrival times, the amplitudes, the frequencies, building a three-dimensional image of Mars from the inside out. It's like creating a portrait using only echoes, only reverberations in the dark. And the picture that emerges is one of a planet more complex than its silent surface suggests. Mars is layered, structured, bearing the signatures of ancient processes that shaped its interior just as profoundly as impacts and erosion shaped its face. In the deep mantle, there may be ghosts. Remnants of ancient mantle plumes, columns of hot rock that once rose from near the core mantle boundary, carrying heat upward like slow-motion fountains of stone. On Earth, mantle plumes create hotspots, volcanic chains, islands born from the depths. Hawaii, Iceland, Yellowstone. Mars had them too, in its more active past. The evidence suggests that plumes may have risen beneath what would become Tharsis, the great volcanic plateau. But unlike Earth, where plumes continue to this day, Mars plumes are extinct. The planet cooled. The convection slowed. The upwelling stopped. Yet their influence remains, frozen into the structure of the mantle itself. Geophysicists detect anomalies, regions where the mantle's properties differ subtly from their surroundings. Ghosts of thermal currents that moved billions of years ago and then went still. Above these ancient plumes, the surface tells its own part of the story. The areoid, Mars equivalent of sea level, the reference surface defined by the planet's gravitational field, shows a pronounced dome over Tharsis. The crust there is thick, the mass immense. The weight of billions of years of volcanic construction has actually deformed the planet's shape, creating a gravitational bulge that spacecrafts can detect from orbit. Tharsis is more than just a collection of volcanoes. It's a monument to Mars' thermal history, a record of when the planet's interior was hot enough, active enough, to force vast quantities of magma to the surface. And that dome in the areoid tells us that the process wasn't brief. It lasted for 1 billion years or more, building layer upon layer, flow upon flow, until the crust beneath could no longer support the weight without bending. Across the planet, crustal thickness varies dramatically. There's a gradient, a pattern to how thick or thin the crust becomes as you move from region to region. The southern highlands have thick crust, sometimes 60 kilometers or more, ancient, primordial, battered by impacts but never fully recycled. The northern lowlands have thin crust, perhaps only 30 kilometers in places, consistent with the idea that this region was catastrophically excavated early in Mars history. This gradient isn't random. It reflects the fundamental division we explored before, the hemispheric dichotomy. But now we understand it not just as a surface feature, but as something that extends deep into the planet's structure. Mars was divided early and thoroughly, and that division reaches from the surface down through the entire crust, perhaps even into the uppermost mantle. It's as if Mars is two half-worlds pressed together, each with its own character, its own history, bound by an ancient violence into an uneasy union. And so we understand now that Mars' stillness is not simplicity. The quiet heart still beats, still holds complexity within it. The core, large and sulfur-rich. The mantle, layered with low-velocity zones and the ghosts of ancient plumes. The crust, fractured and thick and variable, hiding frozen water in its depths. All of this revealed not by digging, but by listening. By patience, by waiting for the planet to speak in the only language it has left, the subtle trembling of a world that has not entirely forgotten motion. As you rest now, imagine yourself floating in that space between the surface and the core, suspended in the mantle's slow warmth, surrounded by rock that has not moved meaningfully in billions of years, yet still whispers of ancient currents, ancient heat, ancient possibilities. Mars' interior is a library of time, each layer a chapter, each seismic wave a sentence we're learning to read. The planet remembers. And slowly, carefully, we're learning to remember with it. The field that fad. Ed. There are forces we cannot see, fields that wrap around worlds like invisible armor. On Earth, we live beneath one such shield, a magnetic field generated deep in our planet's churning core, extending thousands of kilometers into space, deflecting the solar wind, protecting the delicate atmosphere that makes life possible. Mars once had this protection too, but it lost it. And in that loss lies one of the most profound and melancholy chapters in planetary history. Tonight, we trace the story of a field that faded, and what disappeared with it into the cold darkness of space. The dynamo did not die suddenly. This wasn't a light switching off, a heart stopping in an instant. It was a long goodbye, a gradual weakening that may have taken hundreds of millions of years. The dynamo probably shut down in stages, flickering like a flame in the wind, growing weaker, perhaps rallying briefly, then weakening again. We can read this story in the rocks, in the patterns of magnetization locked into Mars' ancient crust. Some regions are strongly magnetic, recording a time when the field was robust and planetary in scale. Other regions, formed later, show weaker magnetization, and some show none at all. It's a timeline written in iron oxide and basalt, a chronicle of decline preserved in stone. The giant impact basins tell part of this story. Hellas, Argea, Isidis. These enormous scars, each hundreds or thousands of kilometers across, were blasted into Mars' surface by apocalyptic collisions. And here's what's remarkable: some of them are unmagnetized. Completely. The rock that melted and reformed in those impacts carries no memory of a magnetic field. This tells us something crucial about when they formed. They must have been created after the dynamo had already shut down, after the global field had faded. If the field had still been active, these basins would have locked in its signature as they cooled. But they didn't. They are blank. Silent. The impacts happened, the rock melted and reformed, and there was no field left to record. Yet the story becomes more complex, more mysterious, when we look at certain young lava flows. Volcanic features that formed much later in Mars history, perhaps 2 billion years ago, perhaps even more recently, and some of them are still magnetized. Not strongly, but detectably. They carry a remnant field. How is this possible? If the dynamo was dead, where did the magnetism come from? Perhaps the dynamo didn't die completely. Perhaps it sputtered back to life occasionally, like embers in cooling ash, generating brief, weak fields before dying again. Or perhaps the magnetism comes from something else entirely, remnant magnetism from the strongly magnetized crust nearby, imprinting itself on cooling lava. Or localized dynamo action in pockets of still molten core. The answer remains uncertain. But the presence of magnetized young flows tells us that Mars' magnetic history is not a simple story of on and then off. It's layered, complicated, full of nuance and exceptions. The crustal magnetism itself records multiple time windows, distinct epochs of magnetic field activity preserved in different geological units. It's like looking at tree rings, each layer telling you about the conditions when it formed. Some crustal regions magnetized when the field was strong and stable, others when it was weaker, more chaotic. Still others show no magnetization at all, formed in the silence after the field had gone. By mapping these magnetic signatures across Mars' surface, scientists can piece together a rough timeline. They can see when the dynamo was most active, when it began to fail, when certain regions of crust formed. It's detective work on a planetary scale, using magnetism as the clue. Today, Mars has no global magnetic field. What remains is patchy and crustal, localized regions where ancient rocks still carry strong magnetic signatures, creating small-scale anomalies that spacecrafts can detect from orbit. These patches are like fossils, the preserved bones of a magnetic field that once lived. Flying over Mars, an orbiter's magnetometer would read near zero in most places. But over the southern highlands, over certain ancient terrains, the readings spike. The crust there remembers. It holds onto the past with a grip that billions of years haven't loosened. These patches don't protect Mars from anything. They're too weak, too localized. But they're evidence. They're proof that Mars was once different, once shielded, once wrapped in an invisible embrace that has long since faded. And what happened when the field disappeared? The consequences were gradual but inexorable. Without a global magnetic field, Mars became vulnerable to the solar wind, the constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. On Earth, these particles are deflected, channeled around our planet by the magnetic field. But on Mars, they strike the upper atmosphere directly. Over millions of years, this bombardment stripped away Mars' atmosphere, molecule by molecule. Ions were accelerated by the solar wind's electric fields and flung into space. The atmosphere thinned. The pressure dropped. Water could no longer exist as liquid on the surface. It would boil away immediately in the low pressure or freeze solid. The loss of the dynamo didn't just remove Mars' magnetic shield. It likely helped strip away the atmosphere itself, transforming Mars from a world where water might have flowed freely into the cold, thin-aired desert we see today. We know this happened because of argon. Specifically, the isotopic ratios of argon atoms still trapped in Mars' atmosphere today. Argon is a noble gas. It doesn't react chemically with anything. It just exists. But it can escape to space, and lighter isotopes escape more easily than heavier ones. When scientists measured the ratio of argon-36 to argon-38 in Mars' atmosphere, they found it skewed heavily toward the heavier isotope. The lighter isotope had been preferentially lost to space. This is the signature of atmospheric escape, proof written in the very air that remains. By comparing these ratios to what Mars' original atmosphere would have contained, based on measurements from Martian meteorites that preserve ancient gases, scientists can estimate how much atmosphere was lost. And the answer is staggering. Mars may have lost the equivalent of a thick Earth-like atmosphere over billions of years. What remains today is a remnant, a whisper of what once was. The field that faded took Mars' sky with it. Slowly, imperceptibly in any human time frame. But inexorably, as the solar wind carved away layer after layer, year after year, eon after eon, until what had been a world with weather and possibly oceans became a world of silence and dust. It's one of the most profound transformations in our solar system's history. And it happened not through catastrophe, but through absence. Through the simple, terrible fact of a magnetic field switching off and never returning. As you rest now, imagine standing on Mars 4 billion years ago, when the dynamo still hummed deep below, when the magnetic field still stretched into space, invisible but present. The sky above you might have been thicker, the pressure higher. Perhaps clouds drifted overhead. Perhaps rain fell, at least occasionally, in a climate warmer and wetter than anything Mars has known since. And now imagine standing in the same spot today. The field is gone. The sky is thin and rust-colored. The pressure so low that your blood would boil. The solar wind strikes the upper atmosphere unimpeded, still slowly carrying away what little remains. Mars didn't die in fire. It faded. Gently. Quietly. The way a light dims when the power slowly drains away. And in that fading, we see the fragility of planetary atmospheres, the importance of magnetic fields, the delicate balance required for a world to remain alive. Mars is a reminder. A beautiful, haunting reminder that worlds can change. That protection can be lost. That silence can fall where once there might have been sound. When water ruled. There is a memory etched into Mars' surface. A memory of movement, of flow, of water carving channels and filling basins and reshaping landscapes in ways that only liquid can. Today, Mars is a desert world, locked in perpetual drought. But this was not always so. Tonight, we journey to a time when water ruled Mars, when rivers ran across ancient continents, when an ocean may have lapped at primordial shores, when beneath the surface, vast reservoirs of liquid water waited in the darkness, and the planet's geology was written not just in stone and fire, but in the language of waves and currents and rain. Mars once had an ocean-like hydrologic system, not just scattered lakes or temporary floods, but a planetary-scale water cycle. Water evaporated from surfaces, formed clouds, fell as precipitation, collected into streams that fed rivers that emptied into basins. It was a system, interconnected and dynamic, operating over millions of years. We know this from the scars it left behind. From valley networks that branch like the veins of a leaf, each tributary feeding into larger channels in patterns that only sustained flow can create. From sedimentary deposits laid down in layers that speak of standing water, of deltas building outward, of shorelines advancing and retreating. Mars was wet. Not everywhere, not all at once, but wet enough and long enough to reshape its surface in profound ways. In the northern lowlands, where the crust is thin and the elevation low, scientists have identified what appear to be ancient ocean shorelines. Contour lines that wrap around the basin at consistent elevations, marking boundaries between what might have been sea and land. These features are subtle. Billions of years of erosion and dust deposition have softened them, but they're there, visible in high-resolution topographic data. Some researchers see multiple shoreline levels, suggesting the ocean's extent varied over time. Perhaps it expanded during warmer, wetter periods and contracted during colder, drier ones. Perhaps it froze and sublimated away, then returned when conditions changed. The exact history remains debated, but the presence of these features is compelling. An ocean on Mars. Not a global ocean like Earth's, but a northern sea, perhaps 1 billion cubic kilometers of water pooled in the Great Basin created by that ancient, catastrophic impact. Where shorelines existed, sediments should have accumulated. And they did. Coastal sediment evidence appears in certain regions. Fine-grained deposits that could have settled from standing water, materials sorted and arranged in ways consistent with wave action and tidal processes. These aren't dramatic features. They're subtle, easily overlooked. But under close examination, they tell their story. Sedimentary rocks on Mars have been studied by rovers, ground into powder and analyzed, their chemistry and texture revealing formation environments. Some clearly formed in the presence of water. Some show layering consistent with deposition in lakes or seas. The evidence is fragmentary, scattered across millions of square kilometers, but each piece adds to the picture. But the most astonishing revelation has come from combining two technologies, radar and seismology. Radar can penetrate Mars' surface, detecting boundaries between different materials based on their electrical properties. Seismology detects those same boundaries based on how they transmit vibrations. When you use both together, the synergy is powerful. And what this synergy has revealed is extraordinary. Mars hosts vast underground liquid water reservoirs. Not ice. Liquid water. Trapped in porous rock formations deep beneath the surface, perhaps 10 to 20 kilometers down, where pressure and residual geothermal heat combine to keep it liquid despite the cold conditions above. These aren't underground lakes in the traditional sense, not open caverns filled with water. They're aquifers, saturated zones where water fills the spaces between grains of rock. but the volume is staggering. Some estimates suggest enough water to cover the entire planet in an ocean 1 to 2 kilometers deep, if it were all brought to the surface. Mars hasn't lost all its water. It's still there, hidden, waiting in the deep darkness beneath the rust-colored plains. How does this water remain liquid? Several water retention mechanisms work in concert. Salts dissolved in the water lower its freezing point, allowing it to stay liquid at temperatures well below 0 Celsius. The pressure at depth also helps. Water under pressure can remain liquid at lower temperatures than at the surface. And geothermal heat, though modest on modern Mars, still provides enough warmth in certain regions to prevent freezing. This water has been there for billions of years, sealed away, preserved like a time capsule from Mars' wetter past. It may have been surface water once, percolating downward through fractures and porous rock until it reached depths where it couldn't escape. Or it may be primordial water, trapped during Mars formation and never released. Either way, it's a reservoir, a hidden ocean beneath a desert world. Ancient water didn't just exist on Mars, it interacted with the rocks around it, transforming them chemically. In the planet's earliest era, groundwater that was neutral or slightly alkaline, not acidic, circulated through the crust and formed clays. Phyllosilicates. These are minerals that only form in the presence of liquid water over extended periods. Rovers have found these clays in ancient rocks, particularly in the southern highlands and in crater walls where impacts have exposed deep, old strata. The presence of these minerals tells us that early Mars had a gentler chemistry than later periods. The water was hospitable, capable of supporting the kinds of reactions that, on Earth, are associated with life. This wasn't brief. Clay formation requires sustained water-rock interaction, thousands or millions of years of groundwater slowly altering basalt into new minerals. Mars was wet for a long time in its youth. In certain regions, particularly around ancient volcanic areas, scientists have detected hydrothermal alteration halos, zones where hot water, heated by magmatic intrusions, rose through the crust and chemically altered everything it touched. These are fossil hot springs, ancient geothermal systems where water and heat combine to create environments that might have been oases for chemistry, perhaps even for life. The minerals in these halos tell stories of different temperatures, different water compositions, different stages of activity. Some formed in boiling water, some in cooler fluids rich in dissolved minerals. Each halo is a snapshot of an active hydrothermal system frozen in time. On Earth, hydrothermal systems are havens for microbial life, places where energy and chemistry combine to create opportunities even in harsh environments. On Mars, they might have been the same. Rivers once crossed Mars' surface. We know this from conglomerate outcrops, rocks composed of rounded pebbles cemented together. These pebbles couldn't have been rounded by wind. They're too large, too smooth. They were rounded by water, tumbling along riverbeds over long distances until their edges wore smooth. The presence of conglomerates proves that Mars had long-distance rivers, flows sustained enough to transport cobbles and boulders downstream, depositing them in ancient stream beds that have since turned to stone. These weren't brief floods. These were persistent flows, perhaps seasonal but returning year after year, carving channels and building bars and creating the sedimentary architecture we associate with river systems. But Mars also experienced violence. Catastrophic releases of water on scales that dwarf anything Earth has ever seen. The evidence appears as streamlined islands, teardrop-shaped hills and mesas carved by megafloods, water moving so fast and in such volume that it sculpted bedrock itself. These floods may have been triggered by the sudden release of subsurface water or ice, perhaps when volcanic heat melted a barrier or when pressure built up until rock failed catastrophically. The water would have surged across the surface at tremendous speed, carrying boulders, scouring channels, reshaping landscapes in days or weeks. The channels that remain, Casey Valles, Ars Valleys, others, are among the largest flood features in the solar system. They're not rivers. They're the scars of apocalyptic deluges. These floods often originated from chaotic terrain, regions where the ground has collapsed into a jumbled mess of fractured blocks and depressions. These collapse zones mark where subsurface reservoirs catastrophically drained, the overlying rock falling into the void left behind. Imagine an underground ocean, sealed beneath a layer of frozen ground for millions of years. Then, something changes. A crack forms. The ice barrier fails. Suddenly, billions of cubic meters of water burst forth, gushing onto the surface, carving channels as it rushes toward lower elevations, eventually pooling in basins or sublimating into the thin atmosphere. The chaotic terrain is the wound left behind, the scar tissue of a planet bleeding water. And then there are the inverted river channels. These are perhaps the most poignant features of all. Once, they were valleys carved by flowing water. Rivers ran through them, depositing sediment along their beds. But over billions of years, the surrounding landscape eroded away faster than the channel itself, because the sediment filling the channel was more resistant than the rock around it. The valley became a ridge. The riverbed now stands above the surrounding plain, inverted, a ghostly echo of water that flowed billions of years ago. Walking across Mars, you might climb a ridge and realize you're standing on what was once the bottom of a river. The water that carved it is gone. The atmosphere that sustained it has been stripped away. But the form remains, inverted, preserved like a fossil of flow itself. Water ruled Mars once. Not briefly, not tentatively, but profoundly. It carved valleys and filled basins. It altered rocks and created minerals. It pulled in vast reservoirs underground where some still remains today, hidden beneath the frozen desert, waiting in the darkness. The water's reign ended. The climate changed. The atmosphere thinned. The rivers dried. The ocean, if it existed, froze and sublimated away or sank into the crust. But the memory remains. Written in stone. Carved into channels. Locked in minerals and sediments and inverted valleys. As you rest now, imagine Mars as it might have been 3.5 billion years ago. Imagine standing on a shoreline, watching waves lap against volcanic sand. Imagine rivers flowing through distant valleys, their waters carrying sediment toward a northern sea. Imagine rain falling from thick clouds, pooling in crater lakes, seeping underground to feed vast aquifers that stretch for hundreds of kilometers. That world existed. Briefly, in geological terms. But it was real. And beneath the surface, in the deep darkness, some of that water remains. Still liquid. Still waiting. A remnant of an age when Mars was not a desert, but a world where water ruled. Ice in motion. Water on Mars exists in silence now. Locked away. Frozen. But ice is not stillness, not entirely. Even frozen, water moves. It flows, slowly, over thousands of years. It shapes the land in subtle, beautiful ways. It carves patterns into the surface that speak of pressure and temperature, of seasons cycling over millennia, of a world where ice is both sculptor and canvas. Tonight, we explore the cryosphere of Mars. The realm where water exists not as liquid or vapor, but as ice. Where glacier once flowed and may flow still, hidden beneath protective blankets of dust. Where permafrost extends kilometers deep, and where the landscape itself has been molded by freeze and thaw, by the patient, inexorable geometry of frozen water. Across vast stretches of Mars, particularly in the mid-latitudes, the surface displays what scientists call periglacial landscapes. These are terrains shaped by the presence of ice just beneath the surface, ground ice that expands and contracts with temperature changes, that sublimates slowly into the atmosphere, that creates distinctive patterns and textures impossible to form any other way. This buried ground ice isn't a thin frost. In some regions, it extends meters or even kilometers deep, a frozen reservoir that may contain more water than all of Earth's Great Lakes combined. Radar can detect it, penetrating through overlying dust and rock to reveal the characteristic signature of subsurface ice, bright, reflective layers that return radar signals with distinctive patterns. The ice has been there for millions of years, perhaps billions in some locations. Waiting. Preserved by the cold. A record of Mars climate history locked in crystal lattices of frozen water. In certain valleys, particularly in the mid-latitudes, strange features fill the landscape. They're called lineated valley fill, patterns of parallel ridges and grooves running along valley floors, flow features that suggest something viscous once moved through these channels. Not water. Ice. These are likely the remains of ancient valley glacier, rivers of ice that flowed downslope under their own weight, carving the valleys deeper, transporting rocky debris, leaving behind the textured surfaces we see today. The lineations mark flow lines, directions of movement frozen in time when the glacier became too cold or too thin to continue their slow advance. Some may still be glacier, buried beneath meters of dust that protect them from sublimation. From orbit, they look like rocky valley floors. But beneath that protective covering, ice may still persist, compressed and ancient, flowing imperceptibly even now at rates measured in millimeters per year. In a region called Dorsa Argentea, near Mars' South Pole, scientists have identified what appear to be eskers, long, winding ridges that snake across the landscape. On Earth, eskers are formed by meltwater streams flowing within or beneath glacier, depositing sediment in channels that become ridges when the ice eventually melts away. The presence of eskers on Mars suggests that glacier once existed here, and more remarkably, that liquid water flowed beneath them. This requires very specific conditions, enough pressure from overlying ice to lower the melting point, perhaps combined with geothermal heat or concentrated salts. But it happened. Water flowed in darkness beneath Martian ice, carving channels and depositing sediment, creating features that endure millions of years after the ice itself has vanished. These eskers are ghosts, remnants of a time when Mars' climate allowed for glacial melt, when ice and liquid water coexisted in ways that seem impossible under today's conditions. Certain craters on Mars have unusual shapes. Ring mold craters, impacts where the ejecta forms a distinctive circular rampart, a raised ridge around the crater's perimeter. These ramparts form when the impacting object strikes ground rich in ice or water. The heat of the impact melts the ice, turning the ejecta into a fluid slurry that flows outward before refreezing, creating that characteristic rampart structure. These craters are markers. They tell us where subsurface ice existed at the time of impact. By mapping their distribution, scientists can reconstruct where ice was present at different points in Mars' history. And the pattern is clear: ice is widespread, particularly at higher latitudes, extending far closer to the equator than current climate models would predict. Mars holds more ice than the surface conditions suggest it should. The planet remembers colder climates, different orbital configurations, times when ice could accumulate even at relatively low latitudes. In some regions, the terrain displays a scalloped appearance, as if someone has taken an ice cream scoop to the surface. This scallop topography forms through sublimation, ice beneath the surface gradually turning to vapor and escaping into the atmosphere, leaving behind depressions where the ice once was. The process is slow, operating over thousands of years, but it's continuous in regions where buried ice exists close to the surface. The ground subsides unevenly, creating those scalloped patterns, hollows separated by ridges, a textured landscape that could only form through the loss of subsurface volume. Walking across scalloped terrain would be like traversing a landscape of frozen waves, each depression marking where ice has been lost, each ridge marking where support remains. The entire surface slowly deflating as its icy skeleton sublimates away. Even stranger is thumbprint terrain, surfaces covered in parallel arcs and ridges that resemble the whorls of a fingerprint. These features are found near Mars' poles and are thought to form through the slow flow of ice-rich material, possibly dusty ice or ice-cemented regolith, deforming under its own weight in patterns that reflect underlying topography and flow dynamics. It's a kind of glacial tectonics, the ice not flowing freely like liquid but deforming plastically over geological timescales, creating compressional ridges where flow converges or where obstacles disrupt movement. The result is these beautiful, mysterious patterns, terrain that looks almost organic, as if the surface itself has fingerprints. Near the poles, other textures emerge. Brain terrain, surfaces with convoluted ridges and valleys that resemble the surface of a human brain. These likely form through differential erosion of layered ice and dust deposits, the polar layered deposits that record millions of years of climate cycles. As ice sublimates preferentially in some areas and dust protects other regions, complex topography develops, creating that characteristic brain-like texture. Each ridge and valley in brain terrain represents different layers, different episodes of deposition, different climate states. Reading brain terrain is like reading tree rings, each convolution holding information about Mars' past, about when ice accumulated and when it eroded, about the rhythm of orbital changes that drive climate on a planet without oceans to buffer temperature swings. Some craters appear swollen, larger than they should be given their age and the normal rate of infilling. These expanded craters form when the ground beneath them is rich in ice. Over time, as ice near the surface sublimates, the crater floor and walls expand outward, the depression growing as volume is lost from the surrounding terrain. It's counterintuitive, you'd expect craters to shrink over time, filled in by wind-blown dust and debris. But when ice is involved, the opposite can happen. The crater becomes a focus for sublimation, the depression itself creating microclimatic conditions that accelerate ice loss, causing the crater to grow even as its surroundings slowly deflate. And then there are pedestal craters, impacts where the crater and its ejector blankets sit atop a raised platform, elevated above the surrounding terrain. These form when an impact occurs in ice-rich ground. The heat of the impact armors the ejector, sintering the dusty material or melting and refreezing ice within it, creating a protective cap. Over time, the surrounding terrain erodes or sublimates away, but the armored ejector resists erosion, remaining elevated. The crater ends up perched on a pedestal, sometimes meters or tens of meters above the surrounding plain. It's an inversion, like the inverted river channels, where what should be lower becomes higher through the differential removal of material around it. From a distance, pedestal craters look almost artificial, these circular mesas topped with craters, monuments to impacts that happened millions of years ago when the ground held more ice than it does today. All of these features, the lineated valleys, the eskers, the scalloped terrain, the thumbprints and brain folds and expanded craters, all of them are the language of ice. They're how frozen water communicates its presence, its history, its slow movements across geological time. Mars is not a dead world of static ice. It's a world where ice has been and continues to be an active geological agent, shaping terrain, creating patterns, recording climate history in forms we're only beginning to fully understand. Beneath the dust, beneath the rust-colored veneer that makes Mars appear so uniform from a distance, there is ice. Vast quantities of it. Moving slowly. Sublimating. Flowing. Creating beauty in its geometric precision, in the way it responds to pressure and temperature and time. As you rest now, imagine standing on Mars at 60 degrees latitude. Beneath your feet, meters below the surface, a layer of ice extends as far as you can see. Pure water ice, compressed and ancient, containing more water than many of Earth's rivers combined. Around you, the terrain is scalloped, textured, marked by the slow loss of that ice to the thin atmosphere. In the valleys nearby, lineated patterns reveal where glacier once flowed, perhaps still flow beneath protective dust. Craters dot the landscape, some swollen, some perched on pedestals, each one telling a story of ice and impact and erosion. The silence is absolute, but the landscape speaks. In textures and patterns, in inversions and depressions, in the slow, patient geometry of frozen water shaping stone. Ice ruled Mars once, in a different way than water. And ice rules still, hidden but present, waiting beneath the surface, holding memories of colder times, of different climates, of a world where frozen water extends from pole to mid-latitudes, an unseen ocean locked in the crust. The ice remembers. And in its memory, we find clues to Mars' past, present, and perhaps even its future. The polar archives. At the ends of a world, where sunlight arrives at its most oblique angle, where temperatures plunge to depths that would freeze carbon dioxide from the air itself, there exist repositories of time. Archives not written in ink or stored in libraries, but laid down layer by layer, year after year, century after century, in ice and dust and frozen air. Tonight, we journey to Mars' poles, to the great ice caps that crown the planet's northern and southern extremes. These are not simple frozen masses. They are books, volumes of climate history stretching back millions of years, each page a thin layer of ice, each chapter a sequence of climate states. And written in their structure, in their composition and their strange, beautiful features, we find the story of how Mars' climate has changed, cycled, and evolved over vast spans of time. The two polar caps are not identical. The north and south poles of Mars differ in fundamental ways, starting with their very composition. The northern cap is primarily water ice, a dome of frozen HO perhaps 2 to 3 kilometers thick at its center, extending across a region larger than Greenland. In winter, a seasonal layer of carbon dioxide frost covers it, but beneath that temporary coating lies permanent water ice, ancient and layered. The southern cap is more complex. It too has a core of water ice, but atop it sits a permanent layer of carbon dioxide ice, dry ice, perhaps 8 to 10 meters thick. This cone never fully sublimates, even in southern summer. The South Pole is colder, receives less sunlight due to Mars' elliptical orbit, and maintains conditions that allow solid carbon dioxide to persist year-round. These compositional differences reflect the planet's orbital dynamics, the tilt of its axis, the eccentricity of its path around the Sun. Mars wobbles and precesses over cycles lasting tens of thousands to millions of years, and these variations drive profound changes in which pole receives more energy, where ice accumulates, where it erodes. Both caps display remarkable internal structure. Layered deposits, stacks of ice and dust laid down in rhythmic alternation, visible in cliff faces and scarps where erosion has exposed the cap's interiors. These layers are climate records, each one representing a period of accumulation, its thickness and composition determined by the prevailing conditions at the time it formed. Scientists have counted hundreds of these layers, perhaps over 1,000 in some locations. Each layer averages tens of meters thick, representing accumulation over periods ranging from tens of thousands to hundreds of thousands of years. The variations in brightness, light layers rich in ice, darker layers containing more dust, reflect changes in Mars' climate, in how much water vapor was available to freeze out at the poles, in how much dust was being blown around the planet. Reading these layers is like reading tree rings, but on a planetary scale. They tell us when Mars' orbit brought it closer to the Sun, when its axial tilt increased and summers became more intense, when global dust storms were more frequent. The layered deposits are archives, histories written in ice that we're only beginning to fully decipher. Across the northern cap, spiral troughs carve through the ice like massive, gently curving canyons. These troughs are hundreds of meters deep, kilometers wide, and spiral outward from near the pole in patterns that resemble the arms of a galaxy. They're one of Mars' most visually striking features, visible even in small telescopes when viewing the planet from Earth during northern summer. For decades, their origin was mysterious. Why spiral? Why this particular geometry? The answer lies in a combination of factors: katabatic winds, cold, dense air flowing downslope from the cap center, interacting with the Coriolis effect from Mars' rotation, preferentially eroding certain areas, creating troughs that then channel winds more efficiently, deepening themselves in a feedback loop. The spiral pattern emerges from the physics of rotation and flow, ice and atmosphere working together over millions of years to carve these magnificent structures. They're not static. They evolve slowly, migrating, deepening, reshaping the cap surface in ways that continue today. The largest canyon in the northern cap is Chasma Boreal, a massive rift cutting deep into the ice, exposing hundreds of layers in its walls. This chasm is over 500 kilometers long, 100 kilometers wide in places, and up to 2 kilometers deep. Standing at its edge would feel like standing at the rim of a Grand Canyon, except the walls are ice and dust rather than sedimentary rock. Within Chasma Boreal, scientists have observed fascinating features: dune fields on the canyon floor, avalanche deposits where ice and dust have broken free and tumbled downslope, and most intriguingly, evidence of ancient volcanic ash layers interbedded with the ice. These ash layers, blown to the poles from volcanic eruptions perhaps millions of years ago, serve as chronological markers, helping scientists establish absolute ages for different sections of the layered deposits. The canyon itself may have formed through catastrophic collapse, or perhaps through focused erosion by winds funneling through a pre-existing depression. Its origin remains debated, but its existence provides an unprecedented window into the polar cap's interior, a cross-section through millions of years of climate history. One of the long-standing mysteries about Mars' polar caps was whether the ice actually flows. On Earth, ice sheets flow under their own weight, deforming plastically, moving from areas of accumulation toward edges where it melts or carves off. But would Martian polar ice, in such cold conditions, flow at all? Or would it simply accumulate, static and brittle? The ice flow mystery has been solved through careful analysis of surface features, crater deformation, and modeling. The ice does flow, but slowly, millimeters to centimeters per year in most places, faster in certain locations where the ice is thicker or the surface deeper. The layered deposits aren't purely a stack of horizontal beds. They've been warped and folded by this flow, creating complex internal geometries. Understanding ice flow is crucial for interpreting the climate record. Layers aren't necessarily in the same position where they originally formed. They've been transported, compressed, stretched. Reading the polar archives requires accounting for this motion, for the way ice behaves as a very slow-moving fluid over geological time. On the southern cap, strange features dot the permanent co-ice. They're called Swiss cheese terrain, flat-top mesas and circular pits that give the surface an appearance reminiscent of, well, Swiss cheese. These features form through differential sublimation. During southern spring and summer, sunlight penetrates the translucent co-ice and is absorbed by darker material below, warming it. This heat causes the overlying dry ice to sublimate from the bottom up, creating pits. Over time, as pits expand and merge, they leave behind flat-top mesas of co-ice between them. The entire terrain is slowly degrading, the permanent cap thinning at rates of meters per Martian year in some locations. This suggests that Mars is currently in a climate phase where the southern co-cap is out of equilibrium, slowly disappearing. Eventually, if conditions don't change, the permanent southern co-cap might vanish entirely, leaving only seasonal frost. Even more dramatic are the spider geysers, officially called a rainiform terrain because the patterns resemble spiders. These features form in a remarkable process unique to Mars. During southern spring, sunlight penetrates the translucent seasonal co-frost layer, warming the darker ground beneath. The trapped co-sublimates, building up pressure until it breaks through the ice layer in explosive jets, carrying dust and sand that is deposited in radial patterns around the vent. The result, over many seasons, is spider-like formations, dark starburst patterns with channels radiating outward from central points. Some of these spiders have dozens of legs, channels carved by repeated geyser eruptions year after year. From orbit, fields of rainiform terrain look otherworldly, like vast colonies of frozen, geometric life forms imprinted on the surface. These geysers are active today. Each Martian spring, they erupt, venting gas and dust, creating dark fans that streak across the frost, then fading as summer advances and the seasonal ice completely disappears. Nearby, other regions display what's called cryptic terrain, surfaces that warm up in spring but don't brighten, remaining dark even though they should be covered in bright co-frost. The mystery was solved when high-resolution imaging revealed that these areas are covered by a thin, translucent layer of slab ice. Sunlight passes through it, warming the dark ground beneath, but the ice itself remains in place longer than regular frost. The result is an optical illusion of sorts. The terrain appears dark because you're seeing through the ice to the ground below, but the ice is still there, invisible except at very high resolution or through careful spectroscopic analysis. Cryptic terrain represents a different sublimation regime, a different balance between transparency, albedo, and thermal inertia. Above the winter poles, clouds form. Not just any clouds, but the polar hood, a massive vortex of water ice clouds that encircles the pole, sometimes covering the entire cap and extending toward lower latitudes. These clouds form when the polar atmosphere becomes cold enough during winter for water vapor to freeze out, creating ice crystals that spiral around the pole in cyclonic patterns. The polar hood is dynamic, thickening and thinning, advancing and retreating with the seasons. It can be so dense that it completely obscures the polar cap from orbital cameras, hiding the surface beneath layers of swirling ice clouds. Interestingly, the polar vortex, the large-scale cyclonic circulation that develops over each winter pole, shows a symmetry between north and south. The northern vortex tends to be more stable, more circular, while the southern vortex is often more elliptical, more variable. This asymmetry likely results from topographic differences, from the fact that the Hellas Basin, a massive impact depression, sits at southern mid-latitudes and influences atmospheric circulation patterns. These vortices channel heat and moisture, affect where frost forms, influence how the polar caps gain and lose mass. Understanding them is key to understanding Martian meteorology, to predicting how the climate system operates on seasonal and longer timescales. The poles are not merely frozen wastelands. They're active, dynamic, complex. Ice flows. Geysers erupt. Clouds swirl in vast cyclonic patterns. And beneath all this activity, the layered deposits preserve millions of years of climate history, a record of orbital variations and atmospheric changes written in ice and dust. As you rest now, imagine standing near the edge of Mars' northern polar cap during summer. The ice extends before you, brilliant white against the rust-colored plains beyond. Behind you, the spiral troughs cut deep into the cap, their walls exposing hundreds of light and dark layers, each one a moment in Mars' climatic past. This is a place of memory, of archives written in ice, of climate cycles playing out over millions of years, recorded in layers that future explorers might drill and analyze, reading Mars past the way we read Earth's through ice cores from Antarctica and Greenland. The poles remember. They hold within them the story of Mars' wandering orbit, its changing tilt, its variable climate. And in that memory, we find not just history, but hints of what Mars might become in the future, as its orbit continues to evolve and its climate continues to cycle through states we're only beginning to understand. A sculpted surface. A planet's surface is never finished. It is canvas and sculpture simultaneously, shaped by forces that work across timescales both catastrophic and patient. Fire builds. Tectonics crack and uplift. Wind carves with the persistence of ages. And time itself becomes an artist, revealing patterns and structures that speak to processes we're only beginning to fully comprehend. Tonight, we explore Mars as a work in progress, a surface sculpted by volcanism and tectonics, by wind and water, by the slow revelation of geological secrets hidden in stone. This is a world shaped not by one force but by many, working in concert and in conflict, creating landscapes of haunting beauty and profound strangeness. Dominating Mars' western hemisphere is Tharsis, a volcanic plateau so massive it distorts the entire planet. This bulge rises 10 kilometers above the surrounding plains, spans 5,000 kilometers across, and contains some of the largest volcanoes in the solar system. But Tharsis is more than just volcanoes. It's a tectonic feature, a region where the crust has been uplifted, fractured, and deformed by processes operating deep within the planet. The Tharsis bulge tectonics are written across the surrounding landscape. Radiating outward from the bulge are immense fracture systems, graben and rifts where the crust has been pulled apart by the uplift's extensional forces. Some of these fractures extend thousands of kilometers, cutting through ancient cratered terrain, creating linear valleys and ridges that dominate regional topography. The uplift wasn't sudden. It built over hundreds of millions of years as magma accumulated beneath the crust, pushing upward, forcing the surface to dome and crack. The weight of all that volcanic material also caused the crust to sink in some places, creating a complex pattern of uplift and subsidence, extension and compression, all radiating from Tharsis like ripples frozen in stone. The most spectacular consequence of Tharsis tectonics is Valles Marineris, a canyon system so vast it dwarfs Earth's Grand Canyon, stretching 4,000 kilometers across Mars' equator, reaching depths of 7 kilometers in places, and spanning up to 200 kilometers wide. This is not a river-carved valley. It's a tectonic scar. Valles Marineris formed through faulting, through the enormous stresses created by the Tharsis uplift pulling the crust apart. The canyon consists of multiple parallel troughs, each one a massive graben where blocks of crust have dropped along normal faults. The walls expose billions of years of Martian geology, layered sediments, volcanic flows, impact breccias, all revealed in cross-section like a geological textbook open to its most dramatic pages. Within the canyon, secondary processes have continued to shape the landscape. Landslides have created some of the largest mass-wasting deposits in the solar system, with debris flows extending over 100 kilometers from their source cliffs. Water may have carved channels in the canyon walls during wetter epochs. Wind continues to erode and deposit material, creating dune fields on the canyon floors. Valles Marineris is not finished. It evolves still, slowly, as rockfall and sublimation and aeolian processes continue their patient work. Not all of Mars' volcanic features are towering shield volcanoes like those in Tharsis. In the ancient southern highlands, strange formations called pate-ray spread across the landscape. These are broad, low-relief volcanic constructs, sometimes hundreds of kilometers across but rising only a kilometer or two above their surroundings. The highland pate-ray are ancient, deeply eroded, and mysterious. They may represent a different style of volcanism that occurred early in Mars' history, perhaps involving interactions with ground ice or surface water. Some show complex caldera structures, nested collapse features that suggest repeated episodes of volcanic activity and subsidence. Their subdued topography results from billions of years of erosion, their original forms softened and worn. But their chemical signatures remain, detectable from orbit, marking them as volcanic in origin even though they look nothing like the dramatic shields of Tharsis. Even the Great Shield volcanoes hide complexity. Pavonis Mons, one of the Tharsis trio, displays radiating ridge systems across its flanks, Pavonis Mons dikes. These are essentially the plumbing system of the volcano made visible. Vertical sheets of magma that once fed surface eruptions, now exposed by erosion or standing proud due to differential weathering, harder than the surrounding volcanic flows. The dikes radiate from the summit caldera like spokes on a wheel, mapping the pathways magma took as it forced its way through the volcanic edifice. Counting them, measuring their orientations, scientists can reconstruct the stress fields that existed when Pavonis Mons was active, understand how magma moved through the mountain's interior. They're beautiful in their geometry, these fossilized arteries of a once active volcano, now standing silent beneath the thin Martian sky. The great volcanoes also bear scars of catastrophic failure. Mons slide scars, massive landslides where entire flanks of volcanic mountains have collapsed, sending debris across the surrounding plains. Olympus Mons, the largest volcano in the solar system, shows particularly dramatic examples. Its base is surrounded by a cliff several kilometers high, and beyond that cliff lie aureole deposits, the jumbled remains of flank collapses that may have involved thousands of cubic kilometers of material. What triggers such collapses? Perhaps intrusion of magma destabilizing the edifice. Perhaps seismic activity. Perhaps simply the weight of the mountain exceeding the strength of the rocks supporting it. On a world with lower gravity than Earth, volcanoes can grow taller, but they can also fail more catastrophically when they do collapse. These slide scars are frozen moments of violence, preserved for billions of years, reminders that even the most stable-seeming mountains are temporary structures in geological time. But if volcanism builds, wind sculpts. And nowhere is wind's patient artistry more evident than in the Yardang fields scattered across Mars' surface. Yardangs are streamlined ridges carved by wind-blown sand, shaped like inverted ship hulls, all aligned in the direction of prevailing winds. On Mars, some Yardang fields extend for hundreds of kilometers, their ridges parallel and regular, testaments to millions of years of consistent wind erosion. Walking through a Yardang field would be like walking through a forest of stone fins, each one shaped by the same relentless winds, each one a few meters to tens of meters tall, separated by troughs scoured down to harder substrate. The regularity is almost hypnotic, pattern repeated endlessly across the landscape. Individual rocks bear wind's signature too, ventifacts, stones with flat faces and sharp edges carved by sandblasting winds. On Mars, rovers have photographed countless examples. Rocks shaped like pyramids, like wedges, faces polished smooth or pitted depending on the rock's composition and the intensity of wind erosion. And wind creates facies, layers, and textures in sedimentary deposits that record different wind regimes, different transport conditions. Sand dunes migrate, their internal layering preserving a record of wind direction and strength. Dust settles in laminations that record seasonal cycles. The entire Aeolian system, from global dust storms to local dust devils, writes its story in the patterns and textures of Martian sediments. In certain regions, the surface displays honeycomb terrain, patterns of polygonal ridges enclosing depressions, creating textures that look remarkably organic, like biological cells viewed under a microscope. These form through various processes: thermal contraction cracking in ice-rich ground, salt precipitation along fractures, differential erosion of layered materials. Each polygon is typically a few meters to tens of meters across, the ridges standing slightly higher than the cell interiors. The effect is mesmerizing, geometry imposed on geology, order emerging from the interaction of material properties and environmental conditions. Even stranger are boxwork formations, networks of thin, intersecting ridges forming grid-like patterns. On Earth, boxwork forms in caves when softer rock erodes away, leaving harder mineral-filled fractures standing in relief. On Mars, similar structures appear on some outcrops, suggesting that groundwater once moved through fracture networks, depositing minerals, and subsequent erosion has removed the host rock, leaving behind the mineralized fractures as delicate webs of stone. These formations are fragile, intricate, beautiful in their mathematical precision. They speak of water moving through rock, of chemistry leaving its fingerprint, of erosion revealing what was hidden. Some outcrops display zebra-striped rocks, alternating light and dark bands that create striking visual patterns. These stripes likely represent cycles: wet and dry, oxic and anoxic, dust-rich and dust-poor. Each band is a chapter in a cyclical story, perhaps related to Mars' orbital variations, to climate cycles operating over tens of thousands of years. Rovers have examined these rocks up close, finding that the bands differ chemically and texturally, that they represent genuine changes in depositional or diagenetic conditions. Reading zebra stripes is like reading varves in terrestrial lake sediments, each couplet representing a cycle, the pattern revealing rhythm in Mars' ancient environments. Across many regions, fractured mounds rise from the plains, hills and knobs intensely fractured, broken into polygonal blocks by networks of cracks. These may be mud volcanoes, features formed by pressurized fluids forcing their way to the surface. Or they may be impact ejecta that has settled and contracted. Or perhaps they're remnants of once continuous layers, now isolated by erosion. Their fractures the result of stress relief as surrounding material was removed. Each fractured mound is a puzzle, its origin debated, its structure complex. But collectively, they add texture to the Martian landscape, breaking up the monotony of plains with isolated hills that invite closer examination. And throughout Mars, particularly in regions of sedimentary rock, layered buttes rise like monuments. These are erosional remnants, the last standing pieces of once extensive layers, sculpted by wind into flat-topped hills with steep sides. Some buttes are kilometers across, hundreds of meters tall, their layers clearly visible in their flanks, light and dark bands stacked like pages in a book. These buttes are time capsules. Each layer represents a depositional episode, a moment when sediment accumulated, perhaps in a lake, perhaps from airfall dust, perhaps from volcanic ash. And the fact that they stand at all means they're composed of material more resistant to erosion than their surroundings, harder rocks, or more tightly cemented sediments. Standing before a layered butte on Mars would be like standing before a cliff of history, billions of years of deposition exposed in cross-section, each layer sentence in the long narrative of Martian geology. The surface of Mars is a gallery of geological art. Volcanism has built monuments of stone and frozen lava. Tectonics has cracked the crust open, revealing its interior. Wind has carved yardangs and ventifacts, has shaped every exposed surface with patience measured in millions of years. Water and ice have left their signatures in honeycombs and boxwork, in zebra stripes and fractured mounds. This is not a dead surface. It's a palimpsest written and rewritten, erased and reinscribed, each process leaving its mark, each force competing with others to shape the final form we see today. As you rest now, imagine standing in Valles Marineris, at the base of a wall 7 kilometers high, layers upon layers exposed above you reaching toward a salmon-colored sky. Around you, wind-carved yardangs stretch into the distance, their ridges aligned like waves frozen mid-motion. Nearby, a layered butte rises from the canyon floor, its stripes clearly visible, each one representing time compressed into stone. The wind whispers through the canyon, carrying red dust, always sculpting, always shaping. Overhead, the thin atmosphere barely scatters light, stars visible even in daytime if you know where to look. Mars is patient. Its surface evolves slowly now, the dramatic volcanism of its youth long past, the catastrophic floods ended, even the wind working more subtly than it once did when the atmosphere was thicker. But evolution continues. The sculpture is never finished. Stone records every touch, every force, every moment in its long, slow transformation. And we, standing on its surface or studying it from orbit, become witnesses to a planetary work of art 4 billion years in the making, still being refined, still revealing new details, still full of mysteries waiting to be understood. A breathing sky. Above the sculpted surface, there exists another world, one of motion and light, of particles suspended and currents flowing, of phenomena both familiar and alien. The Martian atmosphere is thin, less than 1% the density of Earth's, yet it is far from empty. It breathes with the seasons. It dances with dust. It creates beauty in unexpected ways. Tonight, we look upward from Mars' surface, into the salmon-colored sky, and explore the envelope of gas and suspended particles that wraps this world. Here, in the interplay between surface and space, between rock and light, we find a dynamic system that continues to surprise us with its complexity and elegance. Dust is the atmosphere's defining characteristic. Fine particles of iron oxide, silicates, and other minerals, each grain microscopic, yet collectively capable of transforming the entire planet. But how does dust lift from the surface in the first place, in an atmosphere so thin it can barely be felt? The dust lifting processes are multiple and fascinating. Wind stress is the most obvious. When winds exceed certain threshold speeds, they can shake particles loose and loft them into the air. But on Mars, with its thin atmosphere, wind speeds must be higher than on Earth to achieve the same force. Dust devils help. These whirling vortices, essentially miniature tornadoes without rain, create low-pressure zones at their centers that can suck dust directly upward, bypassing the threshold wind speed requirement. And then there's a feedback effect. Once dust is aloft, it absorbs sunlight, heats the air around it, creates convection, which generates more wind, which lifts more dust. The atmosphere can amplify its own dustiness. During global dust storms, this feedback becomes runaway. More dust means more heating, means more convection, means more dust lofted until the entire planet is shrouded, the surface barely visible from space, the sky from the ground glowing a dim orange-red even at noon. Dust devils and towers are common features of Martian meteorology. On any given Martian day, thousands of them spiral across the surface, ranging from tiny whirls just a few meters across to massive towers a kilometer or more in diameter, reaching heights of 10 kilometers into the atmosphere. Rovers have witnessed them directly, photographed them, even driven through them. The sky darkens briefly as the vortex passes overhead. Dust swirls in elegant helical patterns. Pressure drops measurably. And then it's gone, moving across the landscape, its track sometimes visible as a clean path where the low pressure has lifted away the finest surface dust, revealing darker material beneath. These dust devils are efficient. A single large one can lift tons of dust into the atmosphere. Collectively, they may be responsible for maintaining Mars' background dust haze, the constant thin veil of suspended particles that gives the Martian sky its characteristic color. When regional or global dust storms develop, they don't spread uniformly. They propagate in wave patterns, fronts of thick dust advancing across the planet at predictable speeds, creating pressure waves ahead of them that can be detected by weather stations. These dust storm wave patterns emerge from the interaction between dust heating, atmospheric circulation, and topography. A dust front advances, heats the atmosphere, creates winds that lift more dust at its leading edge. The front propagates further. Behind it, dust begins to settle, the heating diminishes, but by then the front has moved on. From orbit, watching a regional dust storm develop is like watching a wave move across an ocean, except the ocean is air and the wave is made of suspended particles that can engulf an area the size of a continent in a matter of days. Mars' atmosphere does something peculiar. It suprarotates. In the upper atmosphere, particularly at equatorial latitudes, winds blow faster than the planet rotates beneath them. Air moves eastward at speeds exceeding 200 kilometers per hour, circling the planet in just a few Martian days. This superrotation phenomenon is still not fully understood. On Earth, our atmosphere doesn't do this. Winds generally move slower than the planet's rotation speed. But Mars' thin atmosphere, its lack of oceans to transport heat, its strong temperature contrasts between equator and poles, all combine to create conditions where atmospheric waves can accelerate the upper-level winds to speeds faster than the surface rotates. It's as if the atmosphere is trying to outrun the planet itself, a thin shell of gas spinning independently, only loosely coupled to the solid world below. Throughout Mars' atmosphere, gravity waves propagate constantly. Not gravitational waves in the Einstein sense, but atmospheric waves, ripples in the density and temperature structure of the atmosphere, created when air is forced to rise over topography or when convection creates disturbances that propagate outward. These gravity waves are invisible to the naked eye, but their effects can be spectacular. They modulate cloud formation, creating repeating patterns. They transport momentum vertically, affecting winds at different altitudes. They can be detected by spacecraft instruments as regular oscillations in atmospheric temperature and pressure. On Earth, gravity waves create cloud streets, lenticular clouds over mountains, and ripple patterns in noctilucent clouds. On Mars, they do similar things, adding texture and structure to what might otherwise be a featureless sky. Near the limb of Mars, the edge of the planet's disk is seen from orbit, clouds often appear. These limb clouds form at high altitudes, perhaps 60 to 80 kilometers up, in the cold upper reaches of the atmosphere where water vapor can freeze into ice crystals even in the thin air. Limb clouds are often first visible at dawn or dusk, glowing in sunlight when the surface below is in shadow. They can extend for hundreds of kilometers, thin wisps of ice high above the planet, marking the transition between atmosphere and space. Their formation is tied to atmospheric circulation patterns that carry water vapor to high altitudes, to temperature minima where ice can nucleate, to the delicate balance of condensation and sublimation in the tenuous upper atmosphere. Over mountains and other topographic features, wave clouds form with striking regularity. When wind flows over a mountain, it creates a wave pattern downwind. The air rises and falls in a regular oscillation. At the crests of these waves, where air rises and cools, water ice can condense, forming clouds. In the troughs, where air descends and warms, the ice sublimates and the clouds disappear. The result is a series of parallel cloud bands stretching downwind from the topographic obstacle, sometimes extending hundreds of kilometers. The spacing between bands reveals information about atmospheric stability, wind speed, and the wavelength of the gravity waves being generated. From orbit, wave clouds are among the most photogenic features of Martian meteorology. Regular, geometric, proof that even in a thin atmosphere, fluid dynamics creates beauty and order. Perhaps most exotic are the noctilucent clouds, discovered by spacecraft studying Mars' mesosphere. These are the highest clouds in the Martian atmosphere, forming at altitudes around 100 kilometers, composed of water ice or possibly even carbon dioxide ice, and visible only when illuminated by sunlight while the surface below is in darkness. The term noctilucent means night shining, and that's exactly what they do. After sunset or before sunrise, when the atmosphere at lower altitudes is dark, these high clouds glow with reflected sunlight, creating ethereal displays visible from the surface if you know when and where to look. Their existence tells us that water vapor, however sparse, can reach even the highest reaches of Mars' atmosphere, that ice can form in nearly vacuum conditions, that the boundary between atmosphere and space is not sharp but gradual, with phenomena occurring at altitudes where the air is scarcely denser than the interplanetary medium. Lower in the atmosphere, water ice clouds create their own patterns. Cloud streaks extend downwind from craters and mountains, the obstruction creating turbulence that seeds cloud formation, the clouds then stretching out in the wind like banners streaming from the topography. These water ice cloud streaks can be tens or hundreds of kilometers long, narrow bands of white against the salmon sky. They shift and evolve with the wind, forming in morning as the atmosphere warms and humidity rises, dissipating in afternoon as temperatures peak. During certain seasons, particularly in the northern hemisphere's summer, afternoon clouds form regularly over Tharsis and other elevated regions, creating predictable weather patterns not unlike the afternoon thunderstorms of Earth's mountains. Though on Mars, without the thunder or rain, just the gentle condensation and sublimation of ice in the thin air. On the surface itself, seasonal frost streaks appear with the changing seasons. These aren't atmospheric phenomena but ground effects visible from space. Dark streaks that appear on sand dunes and slopes as carbon dioxide frost sublimates in spring, the escaping gas fluidizing sand and dust, carrying dark material downslope in miniature avalanches. The streaks are temporary, fading as the frost completely disappears, but they create striking patterns. Dark fingers reaching down dune slopes, spider-like radiating forms, dendritic channels that look almost biological. For weeks during spring, entire dune fields become artworks, decorated with these ephemeral dark streaks that shift and change daily. All these processes, dust lifting and settling, cloud formation and dissipation, frost appearing and vanishing, create albedo variations across Mars' surface. The planet's brightness changes with season and with dust storm activity. Regions that are dark when dust-free become bright when coated with fresh dust. Areas covered by seasonal frost reflect more light, then darken when the frost sublimates. From Earth, telescopic observers have noted these changes for over a century, interpreting them variously as vegetation, as volcanic activity, as dust storms. Now we understand them as the natural breathing of Mars' atmosphere and surface, the seasonal exchange of volatiles, the settling and lifting of dust, the planet's albedo changing like a slow, planetary-scale pulse. And in the highest reaches of the atmosphere, something unexpected occurs: aurorae without a magnetosphere. Mars lacks a global magnetic field, yet spacecraft have detected auroral emissions, glows created when energetic particles from the solar wind strike atmospheric gases and excite them to emit light. How is this possible without a global field to channel particles toward the poles? The answer lies in Mars' crustal magnetic fields, those patchy remnants of the ancient dynamo. Particles from the solar wind, following magnetic field lines connected to strongly magnetized crustal regions, funnel down into the atmosphere and create localized auroral glows. These aren't the great curtains of light that dance across Earth's polar skies. They're more subdued, more localized, appearing over specific crustal magnetic anomalies rather than at the poles. But they're aurorae nonetheless, proof that even without a global magnetic field, Mars can create some of the most beautiful phenomena in planetary atmospheres. From the surface, these auroral glows might be barely visible, faint blue or green shimmers in the night sky, detectable more easily by instruments than by eye. But they're there, a reminder of the solar wind's constant interaction with Mars' thin atmosphere and remnant magnetic fields. The Martian sky is not empty. It's filled with processes and phenomena, with dust and ice, with waves and clouds, with light scattered and refracted in ways both familiar and strange. The atmosphere breathes, inhaling volatiles in winter, exhaling them in summer, dust rising and falling, clouds forming and dissolving, the whole system cycling through states driven by solar heating and orbital mechanics. As you rest now, imagine standing on Mars at sunset. The sky above you transitions from salmon pink near the zenith to deep blue near the sun, opposite of Earth's sunset, where the blue is overhead and the red near the horizon. This is because Mars' dust scatters red light most effectively, flooding the sky with it, while the thickest concentration of atmosphere near the sun scatters blue light forward. Around you, a dust devil spirals across the plane, its column visible against the darkening sky, reaching kilometers into the atmosphere. Overhead, a few high-altitude clouds catch the last light, glowing white against the deepening twilight. As darkness falls, the stars emerge, brighter than on Earth in the thin air. And if you're standing over a strongly magnetized region of ancient crust, you might notice a faint shimmer near the horizon, auroral glow, particles from the sun painting light in the Martian night. The atmosphere is thin, but it is there, breathing, moving, creating beauty from dust and ice and light. A tenuous envelope that connects surface to space, that moderates temperature, that carries water and particles, that makes Mars not just a rock in space but a world with weather, with seasons, with a sky that changes and evolves. The breathing continues. The dust rises and falls. The clouds form and fade. And above it all, the stars watch unchanging as Mars' atmosphere cycles through its ancient rhythms, patient and persistent, in the thin air of a distant world. The companions. No world travels through space alone. Even Mars, isolated in its cold orbit between Earth and the asteroid belt, has companions. Two small moons, irregular and ancient, locked in their own fates as they circle the red planet. They are Phobos and Deimos, fear and dread, named for the sons of the war god in ancient mythology. But there is nothing fearsome about them when you truly look. They are simply there, silent witnesses to billions of years, keeping their endless vigil. Tonight, we turn our attention to these companions, these small bodies that share Mars' journey through the solar system, each with its own mysteries, its own story, its own inevitable destiny. Phobos is the larger and nearer of the two, a potato-shaped moon just 27 kilometers across at its widest point, orbiting only 6,000 kilometers above Mars' surface. It's so close that it completes an orbit in just over 7 hours, racing around Mars 3 times each Martian day, rising in the west and setting in the east, opposite of every other celestial object in the Martian sky. Its surface is dark, ancient, and heavily cratered. But the most striking features are the grooves, parallel trenches that crisscross Phobos terrain, particularly prominent around the largest crater, Stickney. These grooves have puzzled scientists for decades. Are they fractures caused by the impact that created Stickney? Stress cracks that almost shattered the little moon? Or are they related to tidal forces from Mars, slowly pulling Phobos apart? The groove terrain gives Phobos an almost geometric appearance in places, as if someone has etched parallel lines across its surface with deliberate precision. Some grooves are hundreds of meters wide, 10 to 20 meters deep, extending for kilometers across the moon's surface. They're not random. They have pattern, structure, orientation, clues to the forces that shape them. Stickney crater itself, named after the wife of Asaph Hall, who discovered the Martian moons in 1877, dominates one hemisphere of Phobos. It's nearly 9 kilometers across, a third the diameter of the moon itself. The impact that created it should have shattered Phobos entirely, broken it into fragments. That it survived speaks to either fortune or to internal structure we don't yet fully understand. But there are anomalies. Stickney ray anomalies. The pattern of ejecta radiating from the crater doesn't quite match what models predict. Some rays are brighter than expected, others dimmer. The distribution seems irregular. These anomalies might tell us about Phobos' internal composition, about layers of different materials, about how the moon responded to catastrophic impact. Or they might indicate that Phobos is more porous than we thought, a rubble pile loosely held together by its own weak gravity, the impact's energy absorbed and redistributed in complex ways through a fractured interior. Phobos is dying. Slowly, inexorably, it spirals inward toward Mars. The phenomenon is called tidal decay. Mars' gravity raises tides in Phobos, creating friction, dissipating orbital energy, causing the moon to lose altitude at about 2 centimeters per year. That doesn't sound like much, but over millions of years, it compounds. In approximately 50 million years, a blink in geological time, Phobos will reach the Roche limit, the distance at which Mars' tidal forces exceed the moon's own gravity. At that point, Phobos will be torn apart, broken into fragments that will spread into a ring around Mars. For a few million years after that, Mars will have rings. Not grand and permanent like Saturn's, but temporary structures made of Phobos remains, slowly spiraling inward until they rain down onto the Martian surface as countless small meteorites. Phobos' fate is sealed. Its doom is patient but inevitable. Each orbit brings it fractionally closer to the end. Deimos, the smaller and more distant moon, seems more stable. It orbits at 23,000 kilometers, well beyond the Roche limit, and actually gains altitude slowly due to tidal interactions, the opposite of Phobos. Deimos will eventually escape Mars entirely, drifting away into independent orbit around the Sun, though this will take billions of years. Deimos is only 15 kilometers across, smoother than Phobos, with fewer prominent features. Its most distinctive characteristic is its regolith, the surface layer of dust and broken rock. On Deimos, this regolith appears sheet-like, unusually smooth and uniform, perhaps because impacts into the moon's weak gravity field create ejecta that move slowly enough to blanket the surface rather than escaping into space. The result is a covering of fine material, deep in places, that softens Deimos' appearance, fills in its craters, gives it an almost gentle quality compared to Phobos' harsh, grooved terrain. Phobos contributes to Mars' environment in unexpected ways. As micrometeorites strike its surface, as particles are knocked loose by impacts or by Mars' gravity tugging at loose material, dust escapes into orbit around Mars. Over time, This creates dust rings from Phobos, not rings in the visible sense, but tenuous structures of micrometer-sized particles following orbits near Phobos' path. These dust rings are invisible to the naked eye but detectable by sensitive instruments. They represent material slowly bleeding off Phobos, a preview of the ring system that will form more dramatically when the Moon finally breaks apart. Mars itself wobbles slightly in its rotation, and this libration, a small periodic variation in rotation rate, creates signals that can be detected in various ways. One surprising place this signal appears is in dust distribution patterns. Mars' libration signal in dust manifests as subtle variations in how dust settles and accumulates, patterns that repeat with the libration period. It's a delicate coupling between solid body, atmosphere, and suspended particles, proof that everything in a planetary system is connected. The wobble of the planet affects the distribution of dust in its atmosphere, which in turn affects climate, which feeds back to affect surface processes. Nothing exists in isolation. The moons are part of Mars' story, companions on a journey that began billions of years ago when the solar system was young. Whether they formed alongside Mars, were captured from the asteroid belt, or represent debris from some ancient collision remains uncertain. But they're here now, circling faithfully, Phobos rushing overhead 3 times a day, Deimos moving more sedately across the Martian sky. From Mars' surface, they would be spectacular sights. Phobos would appear about 1/3 the size of Earth's moon in our sky, visibly moving, rising in the west and arcing across the sky in just 4 hours before setting in the east. During that transit, you could watch it go through phases, waxing and waning, sometimes eclipsing the sun in brief transits that dim the daylight for a few seconds. Deimos would be smaller, star-like almost, but bright and moving noticeably against the background stars, completing its leisurely eastward journey across the sky over 2.5 days. Whispers of life. There is a question that hangs over Mars, unspoken perhaps, but always present. It's the question that drives missions, that shapes instrument design, that gives urgency to the patient work of rovers grinding rocks into powder and analyzing their chemistry. The question is simple: was Mars ever alive? Not alive in the sense of a living world, but alive in the sense of hosting life. Microbes, perhaps, simple organisms eking out existence in ancient lakes or hydrothermal vents or deep underground where liquid water persisted. Did chemistry ever cross that threshold into biology? Did Mars ever whisper with voices other than wind and stone? Tonight, we explore the clues. The tantalizing hints, the ambiguous signals, the organic molecules and strange structures that might be evidence of life, or might simply be the complex chemistry that occurs on any world with water and minerals and organic carbon. The search for life on Mars is a search for whispers in the noise, for patterns that demand biological explanation when chemistry alone falls short. The first whispers came from meteorites. Specifically, ALH 84001, a chunk of Martian rock blasted from Mars' surface by an impact, wandering through space for millions of years before falling to Antarctica, where it was discovered in 1984. When scientists examined it closely in the 1990s, they found something intriguing: carbonate globules, tiny structures within the meteorite that might have formed in water. More provocatively, these globules contained possible microfossils, microscopic tube-like structures that resembled, to some eyes, fossilized bacteria. They also contained complex organic molecules and tiny magnetite crystals similar to those produced by some Earth bacteria. The announcement created international excitement, but scrutiny followed. Could these features form through non-biological processes? Could they be contamination from Earth? The debate continues decades later, the evidence ambiguous, neither proving nor disproving the biological hypothesis. The carbonate globules remain a question mark, a reminder that the search for past life requires extraordinary evidence, that ambiguity is the norm when studying ancient chemistry from samples that have been subjected to intense shock, cosmic radiation, and potential terrestrial contamination. On Mars itself, a different mystery emerged: methane. Spacecraft and rovers have detected methane plume enigmas, occasional, localized increases in atmospheric methane that appear and disappear on timescales far too rapid for normal atmospheric processes to explain. On Earth, methane is produced primarily by biological activity: bacteria in wetlands, in animal digestion, in organic decay. It's also produced geologically, by reactions between water and certain minerals, or by volcanic outgassing. Both sources are possible on Mars. But the behavior of Martian methane is strange. Plumes appear in specific locations, then vanish. Background levels fluctuate seasonally. The methane should persist in the atmosphere for hundreds of years based on known chemistry, yet it disappears much faster, suggesting either unknown destruction mechanisms or active ongoing sources. The plumes might be biological, microbes deep underground producing methane that finds its way to the surface through cracks and fissures. Or they might be geological, serpentinization reactions in the subsurface generating methane that's released episodically. Or they might be both, different sources in different locations. The methane enigma remains unsolved, a whisper that could be life, or could be complex geology mimicking life signature. When the Curiosity rover drilled into mudstones in Gale Crater, analyzing the organic molecules within, it found long-chain alkanes, hydrocarbons with complex structures. These molecules can form through purely chemical processes, but their presence in significant quantities, their specific molecular structures, raises questions. On Earth, long-chain alkanes are common in biological materials: lipids, waxes, components of cell membranes. Their presence in Martian rocks, especially in mudstones that formed in ancient lake environments, is consistent with either biological origin or with complex organic chemistry in water-rich settings. The rovers have also detected thiophenes, benzene, and other aromatic compounds, an organic richness unexpected in rocks billions of years old, exposed to radiation and oxidation. Something has preserved these molecules, protecting them from destruction, allowing them to persist as fragile records of ancient chemistry. Laboratory experiments have shown that fatty acid preservation is possible under Martian conditions. When scientists simulate Martian chemistry and radiation environment, fatty acids, fundamental components of biological membranes, can survive for billions of years if sealed in the right minerals, protected from oxidation. This doesn't prove life existed, but it establishes that if life did exist, its chemical signatures could potentially survive to the present day, detectable by sufficiently sensitive instruments. The preservation window is open. The evidence, if it exists, hasn't necessarily been erased by time. In some Martian rocks, scientists have identified organic-rich reaction fronts, boundaries where different chemical environments met, where reactions concentrated organic molecules, creating zones of enhanced organic content. On Earth, such fronts are often associated with microbial activity, life taking advantage of chemical gradients to harvest energy. The Martian reaction fronts might be abiotic, just chemistry responding to changing conditions. But they're consistent with biological activity too, zones where hypothetical microbes clustered at the interface between different fluids, different redox conditions, different nutrient availabilities. Perhaps most intriguing are what some researchers call leopard spot biosignatures, textures in certain Martian rocks that resemble microbial mats, laminated structures with millimeter-scale variations that look remarkably similar to stromatolites, the layered structures built by bacterial communities in Earth's ancient seas. The Perseverance rover has imaged rocks with these textures in Jezero Crater, in deposits that formed in an ancient river delta. The patterns are suggestive, but not diagnostic. Similar structures can form through purely sedimentary processes, minerals precipitating in rhythmic patterns without biological involvement. Yet the resemblance is striking. And if these rocks could be returned to Earth for detailed analysis, if we could examine them with the full arsenal of laboratory techniques, cut thin sections and look under high-powered microscopes, analyze isotopic ratios and search for cellular structures, then perhaps we could know. One outcrop, called Bright Angel, has drawn particular attention. Its chemistry is unusual, rich in carbonates and phosphates, minerals associated with biological activity on Earth. Its texture shows fine laminations, layering on millimeter scales that suggest seasonal or environmental cyclicity. Bright Angel formed in water, probably a lake or river environment, in conditions that might have been habitable. Whether it was inhabited remains unknown, but it's a target, a place where the search for biosignatures might prove fruitful if samples can ever be analyzed with the full power of terrestrial laboratories. Across multiple landing sites, rovers have detected evidence of a carbon cycle, variations in carbon isotopes that suggest carbon moved between reservoirs, between atmosphere and surface, between minerals and organic compounds. On Earth, biological activity significantly affects carbon cycling, creating isotopic fractionations that serve as biosignatures. The Martian carbon cycle evidence is subtle, the fractionations small and potentially explained by abiotic processes. But it's there, a hint that Mars carbon didn't just sit static in rocks and atmosphere but moved, transformed, cycled through different forms in ways that at least raise the question of biological involvement. In various locations, scientists have identified hydrothermal vent analogues, rocks that show chemical and textural evidence of having formed in hot water systems, where heated groundwater circulated through volcanic rocks, creating environments rich in energy and nutrients. On Earth, such environments are havens for life, ecosystems independent of sunlight, powered by chemical energy from the water-rock interactions. If Mars had similar systems, and the geological evidence suggests it did, then it had habitable environments even when the surface was cold and dry, refuges where life might have persisted long after surface water disappeared. The evidence suggests an extended habitable window, not just a brief period in Mars' early history when conditions might have been right for life, but perhaps hundreds of millions of years, possibly recurring episodes whenever volcanic activity or impacts temporarily warmed regions, melted ice, created transient lakes and hydrothermal systems. Life, if it arose on Mars, might have had multiple opportunities to establish itself, to adapt, to survive in increasingly harsh conditions as the planet dried and cooled. The window might even still be open, deep underground where liquid water persists in aquifers heated by residual geothermal energy. We don't know if Mars ever whispered with life. The evidence is ambiguous, suggestive but not conclusive, tantalizing but not definitive. Every potential biosignature has alternative explanations. Every interesting molecule might be abiotic. Every texture that resembles microbial activity might be purely geological. But the question remains open. And that openness is itself significant. Mars was habitable. It had liquid water, organic molecules, energy sources, the chemical ingredients for life. Whether chemistry crossed the threshold into biology, we cannot yet say. But it could have. The conditions were there. And perhaps in some deep aquifer, in some protected pocket of the subsurface where water still flows and warmth still lingers, life might persist even now, clinging to existence in the Martian depths, waiting to be found. A quiet ending. Every story must end. Every journey must come to rest. We have traveled across Mars, from its violent birth to its quiet present, from its deep interior to its thin atmosphere, from ancient oceans to frozen deserts, from the search for life to the patient cycles that govern its climate. And now, we arrive at the ending, not dramatic, not catastrophic, but slow and inevitable, the way worlds change when eons pass like heartbeats. Mars' story is not finished. But we can see its trajectory, understand the forces that shape its future, recognize the patterns that will continue long after humanity has turned its attention elsewhere. Tonight, we consider the slow cycles, the deep time that stretches ahead, and the questions that remain open, perhaps forever, in the cold silence of the red world. Mars wobbles. Its axis of rotation doesn't stay fixed but precesses and tilts over cycles lasting tens of thousands to hundreds of thousands of years. These obliquity cycles reshape climate in profound ways. When Mars' tilt increases, the poles receive more direct sunlight in summer. Ice sublimates, water vapor floods the atmosphere, pressure increases, snow falls at lower latitudes. The planet becomes slightly less hostile, slightly more dynamic. When the tilt decreases, the opposite occurs. The poles become cold traps, accumulating ice, starving the atmosphere of water vapor, reducing pressure further. The planet becomes even more desert-like, even more silent. Earth's moon stabilizes our obliquity, keeping our tilt within a narrow range that allows for predictable seasons and relatively stable climate. Mars has no such stabilizer. Its obliquity has varied wildly throughout its history, perhaps reaching 60 degrees or more at times, creating climates utterly unlike anything the planet experiences today. Currently, Mars is in a moderate obliquity phase, its tilt around 25 degrees, similar to Earth's. But this is temporary. The wobble continues. Tens of thousands of years from now, the tilt will change again, and with it, the distribution of ice, the pressure of the atmosphere, the patterns of frost and sublimation that decorate the surface. These cycles will continue as long as Mars orbits the Sun, as long as gravity and angular momentum govern celestial mechanics. The planet's climate will oscillate, never settling into stability, never catastrophically transforming, just cycling through variations on themes of cold, dry, and dusty. Underlying these cycles is a deeper trend: desertification mechanisms that operate on geological timescales. Mars is slowly losing what remains of its atmosphere and volatiles. The solar wind continues to strip away gas, molecule by molecule. Impacts occasionally blast atmosphere into space. Carbon dioxide becomes trapped in polar ice and in carbonate minerals, slowly sequestered from the active reservoir. The planet is drying out, winding down, approaching a state of minimal atmospheric activity. Not quickly, the process operates over millions of years, but inexorably. Each cycle removes a little more water from accessible reservoirs, locks a little more carbon in stable minerals, thins the atmosphere fractionally. Eventually, perhaps a billion years from now, Mars' atmosphere might be thinner still, its polar caps smaller, its dust storms less frequent. The desertification that began when the dynamo shut down and the magnetic field faded will continue toward its logical endpoint: a nearly airless world, geologically dormant, with only the solar wind and micrometeorites to disturb its ancient surface. But this is deep time almost incomprehensible to human minds. On timescales that matter to us, Mars remains as it is, a frozen desert, a repository of planetary history, a place where the past is written in stone and ice, where questions outnumber answers, where mysteries wait patiently for curious minds to unravel them. Open questions remain. Did life ever arise in Mars' ancient lakes and hydrothermal systems? If so, does it persist in deep aquifers? And could we ever find it? What triggered the dynamo shutdown? And could any process restart it? How much water remains in the subsurface? And is it accessible? What exactly is producing the transient methane plumes? These questions might be answered by future missions, by human explorers drilling deep, by laboratories analyzing return samples. Or they might remain mysteries, questions without sufficient evidence to resolve, ambiguities inherent in studying a world from sparse data. Mars teaches patience. It changes slowly, reveals its secrets grudgingly, rewards careful observation and persistent study. It's not a world of dramatic transformation, not anymore. Its age of fire and flood has passed. What remains is the slow work of wind and sublimation, the patient cycling of seasons and obliquity, the quiet accumulation of dust over structures billions of years old. There's a kind of peace in this. A world that has finished its most dramatic chapters, that now exists in a state of gentle decline, where violence is measured in dust storms rather than volcanic eruptions, where water moves as ice and vapor rather than rivers and oceans, where change occurs but slowly, patiently, without urgency. As we end our journey, imagine one final scene. You're standing on Mars at sunset, somewhere in the mid-latitudes where ancient valley networks once carried water toward northern seas. The sun, smaller than it appears from Earth, descends toward the horizon, turning the dusty sky deeper shades of salmon and orange. The temperature, already frigid, plummets rapidly as the thin atmosphere loses what little heat it held. Around you, the landscape stretches in subtle undulations, ancient riverbeds now inverted into ridges, impact craters softened by billions of years of erosion, distant hills barely visible through the dust haze. Overhead, Phobos rises in the west, moving visibly against the background stars, a small irregular shape rushing across the sky. The wind, always present, whispers across stone, carrying dust that will settle and be lifted again, cycling through the atmosphere in patterns established eons ago. In the distance, a dust devil spirals upward, its column visible against the darkening sky, a transient structure that will exist for minutes before dissipating, leaving no trace. The stars emerge as darkness deepens. More stars than you've ever seen, brilliant in the thin air, unwavering without atmospheric turbulence to make them twinkle. Earth is there, a blue-white point of light, brighter than the others, accompanied by the moon as a fainter companion. From this distance, from this cold and ancient world, Earth looks fragile, a bright speck in the vastness, a reminder of warmth and life and complexity. You breathe, through your suit, of course, the Martian atmosphere utterly unbreathable, and feel the quietness settle into your bones. This is what Mars offers. Not drama, not spectacle in the way of active worlds, but depth. History. The weight of time made visible in every crater, every layer, every grain of oxidized dust. Mars is the planet of memory. It remembers its formation, its brief era of warmth and water, the shutdown of its magnetic field, the stripping of its atmosphere, the slow cooling and desiccation that brought it to its current state. And it will continue to remember, holding these memories in stone and ice, long after humanity has come and gone, long after whatever legacy we leave has eroded away. The cycles will continue. Obliquity will vary. Seasons will pass. Dust will rise and settle. Ice will sublimate and refreeze. And through it all, Mars will remain, patient, silent, waiting in the cold darkness between Earth and the asteroid belt, a testament to how worlds can change, can decline, can enter states of quiet equilibrium where time passes but little changes. Thank you for joining me on this journey. We've crossed billions of years and billions of kilometers, explored from core to atmosphere, from ancient rivers to frozen poles, from magnetic fields to the search for life. Mars is a world of logic, geological logic, physical logic, the inexorable logic of thermodynamics and gravity and time. But it's also a world of beauty, of mystery, of questions that invite exploration. As you rest now, let Mars' quietness fill your thoughts. Let the weight of deep time settle gently around you. Let the image of that rust-colored world, cold and distant but real and knowable, accompany you into sleep. We've explored Mars together. And in doing so, we've glimpsed something profound about how planets work, how they change, how they preserve their histories. Mars is a book written in stone and ice, and we're learning to read it, page by patient page, layer by ancient layer. The red world turns silently in the darkness, keeping its remaining secrets, offering its lessons to those who take the time to listen. And perhaps, someday, when humans stand on its surface with their own feet, when we drill into its crust and analyze its ice and search its depths for life, we'll understand even more. But for now, for tonight, it's enough to have journeyed there in mind and imagination, to have witnessed the calm logic of Mars, to have stood, if only in thought, on that distant shore and looked up at the stars, at Earth, and understood that we are part of something larger, a solar system of worlds, each with its story, each with its own quiet ending. Sleep well. Dream of distant worlds. And remember that Mars is out there, turning slowly under alien skies, waiting patiently for curious minds to unlock the last of its mysteries.